Okay, so in this video, I'm going to teach you how to solve problems or perform hypothesis testing on two populations, and we'll focus on the population means with independent samples and with large sample sizes. So the key in performing hypothesis with two populations could be on means and proportions is to identify what type of information that you have, because largely the formulas that you will be using will depend on is it in do we have a do we have samples that are independent or dependent, and if they are independent, do we have large sample sizes. So these are the things that you need to check first before you decide what type of test you're going to use. Okay, so I'll show one example on how to perform hypothesis testing on two populations and with the condition that they have or we have independent samples and with large sample sizes. To make things clear, when we speak of independent samples, it means the samples or the sample groups has no relationship. So in other words, the certain group A or the data that you can get from group A has nothing to do with the data that you can get from another group B. And then if we say large sample sizes, by convention, when we consider a sample size to be large, we say that n must be greater than or equal to 30. So anything less than 30 will be considered a small sample size. Okay, so that is something that we need to agree on before we decide what type of test. Now, take note that in other references, their um, the definition of their large sample size could be n greater than or equal to 25. Okay, but for us, in this video, we will consider large sample sizes to be n greater than or equal to 30. So here we see information from a given study and according to the data that they have. So this is about a study to compare the average time in days of people who take a certain supplement to recover from a common cold compared to people who do not take the supplement. So basically, what we want to see here is whether um, the supplement is effective. And then their data shows that the sample size, meaning the number of people they asked from their survey, is that 50 from the group with the supplement. So these are the people who took the supplement or taking the supplement, and 48 people who said they are not taking any supplement or that particular supplement. And then the sample mean is 5.4. That means these people on the average recover for about 5.4 days, okay, from a common cold, while those people who are not taking the supplement will take them on an average of 7.2 days, with their corresponding um, standard deviations 1.3 and 3.2. So these numbers were taken from the data. Okay, so they compute for the sample mean and then they compute for the standard deviation, and you will have these numbers. So to check whether this will fall under independent samples and large sample sizes, let's check again the data. So basically, the two groups are those people who are taking the supplement and those people who are not taking any supplement. So clearly, these two are independent samples. The first group has nothing to do with the second group, and they're totally different. One is taking the supplement and the other is without or not taking the supplement. So that will qualify as independent samples. Whereas for the large sample sizes, the sample size for the first group is 50, while the other group is 48. And we said earlier that by convention, or at least what we will consider here, is that n must be greater than or equal to 30. And clearly 50 is greater than 30 and 48 is greater than 30. So at the first uh, part of your solution is analyzing what you have, because later on you will have two population means but maybe dependent samples or small sample sizes. So you have to check what type of two populations that you have. Okay, so again, clearly this problem will fall under independent samples and with large sample sizes. So with that, we will just go back to the steps on how to perform the hypothesis testing. In the videos that I will be doing for the hypothesis testing, I'll be using the 5 steps uh, for the procedure. These 5 steps may not be practiced in some references, and they may not even number the steps, but since we are trying to learn the process, for me I think it's better that we have them numbered so that you could easily track whether you are performing all the necessary steps in the hypothesis testing. And in that way, you could also organize your solution or your procedure for the hypothesis test. So suppose what we want to do here is to know, is there sufficient evidence that the use of the supplement reduces the average time required to recover from a common cold at 5% level of significance. So here we see the 5 steps in the hypothesis testing. Number 1, you need to define the parameters. So you have to set the values for the variables. Is it the mu for the population, sigma for standard deviation, and so on. So we have to define the parameters before we can use them, and then state the null and the alternative hypothesis. Null is our HO. Null is HO. So let's write it down. And the alternative hypothesis is our HA, or sometimes referred as H1. Number 2, identify the significance level. Significance level is our alpha. Is it 5%, 1%, 10%? And this depends on the given problem. Also, in number 2, you have to note down any known values. So these are basically what were stated in the problem. Could be in a form of a table, or they are stated values in the problem. So these are known values and information. Number 3 is determine the type of test. Are you going to use the z-test or the t-test? And then in number 3, so once you have identified the z or the t, or the type of test is statistic, you compute for its value. And then you go to number 4. This is where you draw the standard normal curve. So you make a curve and then identify whether you will be doing left-tailed or maybe a right-tailed or a two-tailed test. And this diagram will highly or well depend on the alternative hypothesis or HA. If it says greater than, so if it says greater than, that means you use the right-tailed. If it says less than, you use the left-tailed. And if it says not equal, then you use two-tailed. And then after that, once you have the diagram, you have to identify the critical value or values if you have two-tailed, and locate the test statistic, the one that you found in number 3. You have to locate whether it will fall under the non-rejection region or on the rejection region. And from there, you can already make a decision and then state your conclusion. So let's start with the process or the procedure. So number 1, we need to define the parameters. So let mu1 be the true average recovery time of people taking the supplement. So the true average means this is if we have asked all the people who will or who are taking the supplement, then that is the average time. So do not confuse this average with the sample average. Okay, so the sample average basically came from the samples. So taking the supplement. And then let's assign mu2, the other mean, be the true or the population average recovery time. Of people who are not taking the supplement. Okay. And then step number 1, we still have to add our HO now since we have mu1 and mu2. So by default, because the null hypothesis is the hypothesis with the equality, so by default we should have the average times to be the same. Meaning to say, you take it or you take the supplement or not, the recovery time will be the same. And remember, what we were trying to know here is whether taking the supplement will reduce the average time. So if mu1, so this is where the assigning of the variables is very important. Take note that the mu1 is for the people who are taking the supplement. And then the mu2 is the average recovery time for the people who are not taking the supplement. So if the claim is, or if what we want to test is whether it reduces the time, then we are trying to see whether the mu1 will become less than the mu2. And this H1 or HA is very important, that you have to be very careful with this, because this will make you decide what type of diagram or what type of test you are going to use. And from here, as early as step number 1, you should be anticipating that you will be performing a test, and it is a one-tailed, that is, the shaded region is on the left, or the left-tailed test. And then after that, we go to step number 2, that is to identify the alpha, the significance level, and from the problem it says that we have to perform the test at 5% level of significance. So the alpha must be 0.05. Now in number 2, this is also where we place any known information that were given in the problem. And in this case, what we know is that, so let's get that information. So from the table we have the following information: sample sizes, sample mean, and sample standard deviation. We have 50, 48, 5.4, 7.2, 1.3, 3.2 respectively. And then in number 3, this is where you decide what type of test you are going to use. To know the type of test, we need to check whether sigma is known. If the sigma is known, we use the z. If sigma is unknown, but n is greater than or equal to 30, we still use the z. However, if sigma is unknown, but the n is less than 30, then we have to use the t-test. So as you can see from this process, the first thing that I check is whether the sigma is known. Because when the sigma is known, regardless of the sample size, you have to use the z-test. Okay, so common mistake is that people start to consider the sample sizes without considering whether the sigma is known or unknown. Okay, that is a mistake. You have to check if the sigma is known. If it is known, then you use z, even if it's just 10 for the sample size. But if sigma is unknown, we go and check the sample size. Greater than or equal to 30, you stay with the z-test. Sigma is unknown, n is less than 30, you do the t-test. In this particular example, we could see that we don't have any information about the sigma, so sigma is unknown. So that makes our options either of these two. But when we check the sample sizes, 50 and 48 are both greater than or equal to 30. That means we have to use the z-test. So now that we have identified the type of test that we're going to perform, we will get the corresponding z formula. For two populations, we have x1 bar minus x2 bar minus the mean difference. And I'll discuss what the mu d, the mean difference, will be equal to. And then the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. With sigma 1, the population standard deviation of the first, in this case the people with taking the supplement, and sigma 2 for the group who are not taking the supplement. But again, since sigma is unknown, but the sample size is large enough, these sigmas can be replaced by the sample standard deviation S. So the values that you see here can be used in place of the sigma. So we will use the S. Okay, this mu d is the mean difference, or the difference of the two means. So basically mu d is equal to mu1 minus mu2. And since our null hypothesis is that mu1 is equal to mu2, this means mu1 minus mu2 is equal to 0, because they are the same. If they are equal, when you subtract them, then the value is 0. So the mu d in this case is equal to 0. x1 bar, x2 bar, x bar, we know that's a symbol for the sample mean. So that means x1 is 5.4 and x2 bar is 7.2. So with the formula, we will be placing the corresponding values. So we have the z equal to 5.4 minus 7.2 minus the mu d, which is equal to 0, divided by the square root of s1 our S1 is 1.3, which will be squared over the sample size 50 plus the 3.2 squared over the sample size 48. And we're almost done. Use your calculator to find the exact value. Okay, so the value that I obtained is negative 3.6208. So for now, you have to keep this value. So note this value. We will go back to this number when we set up our step number 4. Step number 4 is about setting the diagram. So let's create our diagram. So that's the normal curve, standard normal curve. And then we refer to our alternative hypothesis to know what type of diagram we are going to use. So if you remember what I said earlier, it says mu1 is less than mu2, and less than means we have to set up a left-tailed diagram. So we go to our step number 4, make that diagram. So we have on the left, so this is our critical region. So this set of numbers, critical region, which is also our region of rejection, region of rejection or rejection region. That if the number that we have in the step number 3 will fall in this region, then that means we have to reject the null hypothesis. But before that, we need to know exactly the boundary, this number which is our critical value. To know the critical value, we have to refer to the given alpha. The alpha is 0.05 because this test is done at significance level 5%. So at 5%, so we have 0.05. That means we have to know what is the z of alpha or z of 0.05. So take note that some examples will require you to take the half of the alpha, but this is only the case when the test is two-tailed. So that means half of the alpha will be here, that's alpha over 2, and another alpha over 2 will be on the other side. But since this is a one-tailed test, then all the alpha is concentrated on this side. Now, so you need to refer to a list of z. Okay, you can easily have a copy of this online. So find like the z of 0.05. You can even type in z of 0.05 online. It will give you the exact number. Now in the case of my students, they already have a list of special z values that if they just refer to that list, they look for z of 0.05, whatever the number is indicated there, then that's a number that they have to use. Okay, so if I base it from what I have right now, the z of 0.05 is 1.645. Okay, so this number will be placed in our diagram. Now note that in the list it is a positive number, but we should always remember that in the standard normal curve, this is 0. So any number on the left side of 0 will be negative. So at this point, this is negative 1.645. Okay, so once we have plotted that number, we are ready to refer to our test statistic value, the one that we obtained from step number 3. So it says negative 3.6208. Negative 3.6208 is on the left side of negative 1.645. So here, somewhere here, is our negative 3.6208. So that means our decision must be, because the number will fall under the critical region, and that's in the region of rejection, conclusion is reject HO. We have, or there is, we have sufficient evidence to support our H1. So support that mu1 is actually less than mu2. So if the time, this is the average time that the people who recovers from common cold taking the supplement, so it's faster, so it's smaller, so it's faster, so mu1, so that means the supplement reduces, the taking of the supplement reduces the recovery time. So we have shown that it is effective. Okay, so it will not totally make the person immune, but if the person will be infected by a certain cold, then, or by the common cold, then that means if he is taking a supplement, then he will recover faster. Okay, so that's how you perform a hypothesis test. So it is divided into 5 steps. So let's just make a quick summary. The first one is to by assigning the parameters. We have the mu1 and mu2. Then we set up the null and alternative hypothesis. So you should practice on how to create this null and alternative hypothesis. The number 2 is setting the alpha, or checking what's given as an alpha. In this case is 0.05, and take note of some important information. Number 3 is identifying what type of test, which is highly dependent on the availability of sigma. If sigma is known, use Z. Sigma is unknown, check the sample size. Once you have decided what type of test, you get the corresponding formula, place all the values, and then you will get the test statistic value, like in this case, negative 3.6208. Number 4, you set the critical region, which is also dependent on H1. So it's on the left, it's a left-tailed test. Find the critical value, then you place the test statistic value with respect to the critical value. Is it on the left side or right side? And then you decide whether you are going to reject or fail to reject. The number falls to the left of the critical value, so the conclusion was to reject HO. So that means we can no longer believe that, or we cannot consider the recovery time to be the same, and one is faster than the other. Okay, so it's important as well to make a sentence to state your conclusion, not just only saying that it's rejected. Okay, so you should be able to make sense of that statement, reject HO, and then what about rejecting HO? This is because we have, so this is we have sufficient evidence to support that mu1 is less than mu2, meaning the supplement reduces the recovery time, or the taking of the supplement reduces the recovery time. Okay, so that's for the hypothesis testing on 2 population means with independent samples and large sample sizes. That's it.